Hi, grade 11s. We're going to finish up the enzyme notes today. So if you can turn to the bottom of page 10, that would be great. So yesterday we talked about the idea that the enzymes were biological catalysts, so they sped up the chemical reactions that happen in your body without being used up. And they do this by basically taking the reactants, which we call substrates, and orienting them in the right way and binding them so that they are held together long enough in the exact right spot to form a bond or break a bond. And we call that the enzyme substrate complex. So we're going to talk a little bit more today about how enzymes work. So they used to think enzymes worked like a lock and a key. One enzyme would catalyze one specific reaction. And so because the molecules in question are all so small and the reactions happen so fast, we've never clearly seen how enzymes work. So we have a good model. So the original model was called the lock and key theory, has been more recently kind of superseded and updated by a slightly more sophisticated model called the induced fit model. So basically the lock and key theory says the enzyme and substrate meet during the reaction and they fit together perfectly from the very beginning like a lock and a key. And just like one key fits in one specific lock, one enzyme catalyzes one specific reaction. While this model is basically correct, we now believe that instead of always remaining rigid, the enzyme actually changes shape slightly, and that's called a conformational change. So it changes shape slightly when it binds the substrates in order to get a better or tighter grip on the reactants. Okay, so it'll kind of either, if it looks like this, to bind the reactants, it'll either kind of change shape and kind of push in and squeeze it together to get a better grip on it, or if it was one piece that it was breaking apart, it would kind of pull it apart a little bit. So the modification of the lock and key theory is known as the induced fit theory. So upon binding, so once it's bound, the enzyme undergoes a slight conformational, which means shape change, and that'll help more perfectly bind the substrate. Then the reaction takes place, that enzyme substrate complex separates, and the enzyme reassumes its original shape, and it's now free to catalyze another reaction. So how does an enzyme work? Okay, so in addition to that, basically what it does is it lowers the energy required, called the activation energy, for that reaction to proceed. So activation energy is defined as the energy that must be supplied to cause molecules to react with one another. And I always like to tell students to think of it basically like a match, right? When you light a match, you use that striker on the side of the matchbook or on the side of the matchbox. And when we do that, it's fairly easy to light a match, right? That striker kind of acts like the enzyme. It's just the right amount of kind of grittiness to cause the right amount of friction to light the match. So that kind of lowers the amount of energy we have to put in. Now think of the fact that you've got one match, but you don't have that striker surface. So now you've got to go around the room trying to figure out what might be the exact right kind of grittiness to strike that match on to light it. Okay, so just like that striker surface lowers the activation energy, that's what an enzyme does. So if we look at our graphs here, if we look at this graph on the left here, here's our energy level, and this is the progress of the reaction on the bottom. So without enzymes, it would take a lot of energy for those molecules that are just, again, randomly in your bodies to collide in just the right kind of orientation with just the right amount of force to actually bind together or break apart to make that product. With the enzyme, so if we look at the graph on the right, with that enzyme, because it holds it in just the right orientation for just the right amount of time, it takes much less energy, just a little bit of energy compared to all the energy over here for that reaction to proceed. So enzymes lower the activation energy by bringing the substrate molecules together and holding them for long enough for that reaction to take place. There are different factors that can affect enzyme activity. So enzymes are proteins, and the same set of things that affect proteins affect enzymes as well. So since the shape of the enzyme determines the shape of the active site, and that determines their function, anything that changes the shape of the enzyme will affect the enzymatic yield, or the amount of product. So the enzymatic yield would be the product. Okay, so if you think back to when I went over proteins, proteins had 4 levels of structure. The primary structure was that amino acid chain, and then that started to kind of either twist on itself or fold back on itself for the secondary structure. Then the whole molecule felt, kind of changed shape and bonded to itself. And then the 4th level structure were many polypeptide chains bonding together. So anything that causes those weak hydrogen bonds or sulfide bonds to break will change the shape of the enzyme, and that's going to affect the enzyme's ability to do its job. So pH. So most human enzymes prefer a pH between 6 and 8. So some exceptions are things like pepsin in the stomach that likes a pH of 2 and trypsin in the small intestine. So if the pH is too low or too high, the enzyme denatures. And a denatured protein is one that's lost its normal shape. So therefore, it loses its ability to form that enzyme substrate complex. The second one is the temperature. So temperature is kind of a tricky one because if we decrease the temperature a little bit, it's going to slow the rate of the reaction just because the molecules are going to be moving slower. Okay, so lower the temperature, the lower the rate of reaction. But low temperatures don't normally denature or change the shape of the enzymes. However, increasing the temperature is a little bit different. If we increase the temperature ever so slightly, the enzyme will at first increase the rate of reaction and product formation. So a little slight increase in temperature will actually speed up the rate at which the molecules are moving and they bump into the enzymes. But that has to be within the enzyme's normal operating range. So an increase in temperature or a slight increase in temperature will increase the rate of reaction. However, if we increase the temperature too high, so above about 45 degrees Celsius, it'll denature the enzyme or change the shape of the enzyme. So this is why if we are stuck out in the cold, we can kind of often come back from hypothermia. But if we leave, say, those tragic cases where babies are left in cars, you can't actually, they die because their temperature gets too high and their enzymes change shape. Okay, so again, temperature, a low temperature doesn't usually change the shape of the enzyme. Increasing the temperature slightly will increase the rate of reaction, so it'll increase the amount of product that's formed. But if it's too much, but if we increase that rate too much, so above about 45 degrees Celsius in the human body, the enzymes will start to change shape, and that's called denaturing the enzyme. So if we look here, if enzyme is supposed to look like this, and this kind of red piece fits in perfectly, if the temperature gets too high, oops, wrong one, temperature gets too high, then it changes shape, and now it doesn't fit. This is product, this isn't going to know, or this reactant's not going to know that that's the right enzyme, right? So again, it changes shape. It goes from looking something like this to kind of looking different, right? And then without that shape of that active site formed properly, it won't bond the substrate properly. Other things that affect enzyme activity is the concentration of the substrates. So if the concentration, again, those square brackets mean concentration in science, if it increases, the amount of product will increase as well. The rate of product formation will usually increase. However, after a certain amount of time or certain concentration, the rate's not going to increase anymore, as all the enzymes are saturated with substrates and can't work any faster. So it's kind of like being at Superstore on a Saturday morning, okay? If they only have one cashier open, and then they can open up more cashiers, that'll increase the rate of the reaction. But at some point in time, all the cashiers are open, they're working as fast as they can, so you still need to wait in line. Okay, concentration of enzyme. This is usually what limits the overall rate of the reaction. So provided there's adequate substrate, and there usually is millions more substrate molecules than enzyme molecules. The more enzyme you add, the more product you get. The less enzyme you have, the less product you get. So in other words, if the enzyme concentration increases, the rate of product formation will increase as well. If amount of enzyme decreases, the rate of product formation usually decreases as well. So the rate's only going to level off if you run out of substrate. So basically, as you increase, the amount of reaction, eventually you're either going to run out of enzymes or substrate, and then the reaction rate's going to level off, just like the little graph I drew. The last one, this is kind of in brackets, presence of inhibitors. We're not going to kind of test on this, but doesn't hurt you to know it. So inhibitors are molecules that bind to the enzyme in some way to prevent or reduce the rate of substrate binding in the enzyme. So if we look here, here's the enzyme substrate complex. here's my enzyme, there's my substrate, it's going to bind in there. These things are called inhibitors. Okay, if they bind to the active site, it blocks the active site from the real substrate. So no product can be formed. So if the inhibitor doesn't leave, that enzyme is dead. And this is how some kind of poisons or toxins work. Okay, so a competitive inhibitor is when another molecule, usually like a competitor, binds to the active site in place of the substrate. So that's just like here, this enzyme inhibitor complex that we have above. An allosteric inhibitor or inhibition is when a molecule bonds to another site on the enzyme. But another site on the enzyme, it changes the shape of the active site so the substrate doesn't fit anymore. Okay, so if the enzyme is supposed to look like the E, right, maybe there's another bonding site here, and when that molecule bonds, it changes the shape of the active site, so then the reactants or the substrate can't bond. Other times it's more like this, right? It'll block part of the active site, and then the reactants or substrates can't bind as well. Okay. That's all for today. You can work on task 4, which is pages 13 and 14 in your book. Thanks very much.